My name is Henrique Nogueira Pinto. I'm a third-year PhD student in Amsterdam UMC, and I've been fascinated by the brain since I was a little kid. It gives us conscience, it gives us who we are, but in many neurodegenerative diseases, this part of ourselves is lost. And this is a complex thing that is not replicated in any other animal, and that's why we need to model it as well. But it's not only the consciousness that gives us special phenotype in the brain of a human, it's also the cellular structures that give rise to, for instance, the blood vessels. The vessels in our brain are very specific, very different than the blood vessels of the rest of our body. And this difference is called the blood-brain barrier. The blood-brain barrier, or BBB, is a multicellular system that comprises of endothelial cells, pericytes, and astrocytes. Endothelial cells line up the entirety of the blood vessel, and pericytes and astrocytes are there to support the vessels themselves. In many neurodegenerative diseases, such as Alzheimer's, we have a damage of these blood vessels in a very early stage. And what we want to do in our lab is to replicate this system in a humanized way in order to circumvent and find treatments for these diseases. We cannot look at animal models and think they are similar than us, because they are not. That's why in my group we try to change this and don't work with animals. To model the human BBB, we used cells that were donated by healthy controls or diseased patients. With these cells that are either from the blood or from the skin, we can de-differentiate them back into a stem cell. And a stem cell has the capacity to differentiate virtually into any cell type of the blood, of the brain, or of any other organ. With these iPSCs, that's what we call it, induced pluripotent stem cells, we can generate endothelial cells, pericytes, and astrocytes that are representative of the human BBB. In my work, I have optimized and developed a new method to generate brain endothelial cells from stem cells, from iPSCs. But of course, the brain is very complex, and this complexity can only be achieved if we use 3D structures. And this cannot be replicated in the two-dimensional cultures that we usually have in the lab. These 3D structures are called organoids. Organoids are 3D cellular structures that recapitulate some of the morphological and cellular characteristics of our brain. And now that we have our organoids and our brain endothelial cells, we can place them in an organ-on-chip that looks like this. A microphysiological system where we can fine-tune some properties, for instance the location or the flow rate, that is very important to mimic the blood that is happening at the level of the blood vessels. And this is the basis for the Connect project. We want to build a BBB on chip, where we have one side channel with blood-brain barrier endothelial cells, pericytes in between, and then a brain organoid sided to this system. This way, we have all the cell types that we need in order to mimic fully the blood-brain barrier and also the brain itself. And this can be used for two different purposes. We can get a disease model that we can fully recapitulate a different disease, such as Alzheimer's disease or Parkinson's disease, by using cell types of these diseases. Or we can also do drug development and drug testing by perfusing different drugs or different compounds into the BBB side and then see how they cross the BBB and interact with the brain organoid. We want to develop a method that can be used to study and to test different drugs for different neurodegenerative diseases. This way, we can improve the quality of life of patients and, of course, saving animals in the process.